Okay, we're going to talk about polarization just a little bit. If we have light coming along in this direction, this is the direction of propagation. We're just going to look at the electric field in the light wave. The electric field is perpendicular to the direction of propagation. It could be in any direction with respect to the direction, any direction perpendicular to the direction of propagation, and it's generally just mixed up in all possible directions. Now, if we run the light through what's called a polarizing filter, now the polarizing filter has an axis of rotation that's perpendicular to what amounts to a bunch of little tiny horizontal wires, continuous horizontal wires through the glass. Actually, if you had little horizontal wires, it would have the same effect as the polarizer, because what would happen is the electric field that goes back and forth here would cause electrons to move back and forth in the little wires and dissipate the energy of this electric field, so that no electric field in this direction remains. And even a vector that has a partial direction in this direction is going to lose the part of its direction that's parallel to these wires, and all that's going to be left is the straight up and down component of the electric field, which is parallel to what we call the axis of polarization. The axis of polarization is perpendicular to these little wires. They're not really wires. I'm not even sure what all methods are used in creating polarizing filters. But the idea is to damp out the whole component of the electric field in this direction. And that's the result it has. So you end up with polarized light whose electric field is only in the vertical direction, as depicted here. Of course, you can rotate the filter so the wires are going in this direction, and then you'd have all the vectors being perpendicular to those wires. The axis of polarization would change. Wherever the axis of polarization is, that's the direction in which the light is polarized. Okay? So, we say that the electric field comes out vertical. The horizontal component is absorbed by these so-called wires. They're not really wires, but they're more or less channels in which electrons can be caused to move back and forth and dissipate the energy. In this case, the electric field will be oscillating up and down here. Actually, here it might be up, but as we go along with the wave, as we follow this point of the wave along, the electric field will collapse down to zero, go down to negative, come up to zero, come up to positive, down to negative, and so forth. So this is really indicating a simple harmonic motion, essentially, of the electric field with some amplitude. That amplitude we call E max, the maximum value of the electric field, multiplied by the J vector, which is the vertical vector, perpendicular to the line of to the direction of rotation, and then times the cosine of omega t minus kx, because that's what we use for the propagation of the wave. The magnetic field will be perpendicular to the electric field in the I direction, the direction of the I vector, which is perpendicular to the J vector. The electric and magnetic fields are 90 degrees out of phase. And that's the nature of polarized light. Light's polarized in one direction.